Rahul here again from MySlate, and here we will continue our discussion on derivatives. In the last session we had looked at the definition of derivatives. We had tried to define derivative of a function at a point as the slope of the tangent to its curve at that point, and we had introduced these definitions, these notation df by dx, and this the fact that derivative could be defined as the limit as s tends to 0 of delta f by delta h around this point that we are talking about. Okay, so let us try to conclude that by introducing some alternative notations for derivative. So we use f prime x, we have already seen that. We also use df by dx, and because we express fx as y often, so we also use y prime for derivative, and therefore dy by dx. So any of these can be used to indicate derivative of f. And if you not talk of a particular point x equal to e, you talk of any general point x, you could have a general definition for derivative like this, that it is the limit of this ratio delta f by h as h tends to 0 around the point x. So delta f here becomes f at x plus h minus fx. And if you want to find out the derivative of f at x equal to a particular point, say e, you simply substitute x equal to e in whatever expression you get from here. Okay, let's now look at some examples to understand this visually. So we have a constant function here, fx takes a constant value c, and let's look at this orange curve here. It's fx equal to 4, that's the value it takes, and let's try to intuitively see what its derivative would be at different points. So here you can see that whatever value of x you consider, if you try to draw a tangent to this orange curve, you will always get a horizontal line, and the slope of that is 0, no matter what the value of x is, right? So that's what we have here. The derivative of fx here is 0 at every point, every value of x, and that's what we represent here by this gray line. The gray line is nothing but it represents the value of 0. It is the x-axis. So the same thing we can derive through the basic formula that we just learned in the previous slide. So we have this formula of the derivative f prime x, and you substitute these two values. So what is the value of f at x plus h? Well, it is a constant everywhere, so it is c. What's the value of f at x? It's again c, and these two cancel out and you get 0 here. And look at this other example here, fx equals x. This is the identity function. The straight line here, the orange line, which makes an angle of 45 degrees from the x and from the y axis. And here again we can intuitively see that no matter what the value of x is, if you try to draw a tangent to this orange curve, you always get the same slope, right, which here happens to be the slope 1, right, and that's what we have shown here in the orange curve. That is the graph of f prime x. That's the graph of f prime x equals 1, and we can see that also from the basic formula. We have f at x plus h equals x plus h, because this is an identity function here. F at x equals x, and this x gets cancelled with this minus x, and you have h by h. Now here please note that we can cancel these two h in the numerator and denominator, because h tends to 0, but it does not. We are not talking of values of h equal to 0, right? H does not take a value 0. We are talking of values of h close to 0 but not equal to 0, and that's the reason that we can cancel h out in the numerator and as well as in the denominator, and then we get this value of 1 here. Okay, let's look at a generic formula, a generic function, fx equals x power n, and let's try to quickly derive the expression for its derivative. Okay, we'll use the basic formula of f prime x, and we know that it is limit of delta f around x, which is fx plus h minus fx whole divided by h. H is the small interval on x axis around the value x, and we are looking at a very small interval, which means h tends to 0. And we can now substitute this expression here, use the binomial expansion and try to arrive at a neat formula using some simple algebraic manipulations. And let's look at that here. So we have this, and as I said, x plus h raised to the power n could be expanded to using the binomial formula to this. So here, for example, first term is x raised to the power n, the second term is nc1 times x raised to the power n minus 1 times h, and so on. And now you see that this first term here, x raised to the power n, and this term here, minus x raised to the power n, get cancelled, and all we have is these terms which contain h to the power of at least 1. And therefore, we can cancel this h out in the denominator, which with all those h that that appear in the terms on the numerator. And note again that we can cancel these h because h does not take a value 0 anywhere. We are talking of values of h very close to 0, but not equal to 0. And when we do that cancellation, we get this. And from the first term, we take h out, so we have nc1 times x raised to the power n minus 1. So that becomes n times x raised to the power n minus 1. And then we have these other terms where we have h appearing as a multiple with some power, which is at least 1. For example, here we had h square, and one h gets cancelled with the denominator, so we are left with h raised to the power 1, and so on. So now it's pretty straightforward. There is no denominator here. So we simply can substitute h equal to 0, and we get a very neat expression for the derivative of x raised to the power n. It happens to be n times x raised to the power n minus 1. So let's look at some applications of this, but before that, note that although we had assumed here that n is a natural number on this power, but this formula holds for any n, not only natural numbers. So that makes it very generic. Look at some examples. So here fx is equal to 3x, and a constant times a function, and the derivative of that would be that constant times the derivative of that function. So this is 3 times the derivative of x, and we know that derivative of x would be 1. Why? Because x it is nxn minus 1. So which means 1 times x raised to the power 1 minus 1. So that becomes 1, right? So therefore f prime x is 3. And you can see that here that this fx is 3x represents this orange curve, and it has a constant slope everywhere, and that is a slope of 3. And that's what we have shown here in this gray curve. This gray curve represents the derivative of this function with this orange curve. And look at this other example. Fx is x squared, and derivative of that would be 2 times x raised to the power 2 minus 1. So that's 2 times x, which is a straight line. So you have this orange curve of the function f, and you have this gray curve, which is straight line, which is the curve of the derivative of that function. And you can see here intuitively that in the orange curve on the negative x side, you see that the slope of the tangent is always 0, and as you move closer to x, the slope becomes the slope is always negative, right? And the slope becomes less negative as you move closer to 0, and that's what happens here. You see that this gray curve, which is the curve for the derivative, it is negative for values of x less than 0, and it becomes less negative as we move close to 0. And what happens at x equal to 0? Well, this orange curve flattens out, right? So you get a slope of the tangent that is 0, and that's what you see here. This gray line, it crosses the origin, which means at x equal to 0, the derivative is 0. And for positive values of x, you see that the slope of the orange, the tangent to the orange curve, it is positive everywhere. And as x becomes more positive, the slope becomes even more positive. It becomes sharper. And that's what we see in this gray line. It's positive. That's the line for the slope. Okay, so similarly here we have a function which is x cube here, right? And the slope, and this gray curve is the slope of is the curve for the derivative of that function. Incidentally, this is not a straight line here, right? Because why? Because you can see from the formula that we had derived in the last slide, the derivative of x cube would be 3 times x raised to the power 2 minus 1, which is x raised to the power 3 minus 1, which is 3 times x squared, right? So that is the this graph that you see here, the gray curve. And you can again see intuitively that for negative values of x, the slope of tangent to this orange curve is positive, and it becomes less positive as you move closer to 0, and that's what is happening here on the gray curve, right? Its value is positive, but it becomes less positive, and at x equal to 0 this orange curve flattens out, the slope becomes 0, and on the positive side of the x again the slope becomes positive, and as x increases the slope becomes even more positive. Okay, and now let us see this interesting function. This is the modulus of x, and we see that for negative values of x the slope is -1. So the curve of f prime x would be a constant -1. For positive values of x the slope is +1, and therefore we have this different curve here of f prime x. It is equal to +1. So what happens at x equal to 0? Well, that is interesting. That there we introduce the notion of differentiability. At x equal to 0, we see that while the function is defined, as we approach x equal to 0 from the left hand side, we get a value of derivative of the function which is -1, which basically means that the slope of the tangent to the curve, orange curve, is -1. What happens when you approach x equal to 0 from the right hand side? Well, then the derivative of the function takes a value +1, and that's the slope of the tangent to the orange curve as you approach x equal to 0 from the right hand side. So what we have here is two different slopes, two different values of derivative of f as we approach x equal to 0 from the left hand side and from the right hand side. So we say here that there is no unique derivative of this function at x equal to 0, and therefore the derivative does not exist. This function is not differentiable at x equal to 0. It is differentiable everywhere except x equal to 0 because it does not have a unique derivative value. Its derivative does not exist, which means the same thing as it does not have a unique slope of the tangent to its curve as we approach x equal to 0 from the left hand side and from the right hand side. Okay, this is another function, slightly more complicated, but we can apply the same formula that we have learnt earlier. We can take the derivative of each of these terms and then add them up and get the total derivative here. And you can see this on the graph. The orange curve is the curve for the function, and the gray curve, which here happens to be a straight line, is the curve for the derivative. Okay, let's now look at this trigonometric function sin x, which is shown by the orange curve here for different values of x, and it happens that the derivative of sin x is cos x. And first let us try to appreciate that intuitively. I have drawn this cos x curve by this gray line here. Now let's look at a few values of x. When x is 0, what is the slope of the tangent to the orange curve? Well, it seems to be a positive slope. In fact, it happens to be exactly 1, and that's what we have here on the value of the gray curve. That's the curve for the derivative. It takes a value 1. What happens when x is pi by 2 to the function? Well, its curve flattens out a little bit temporarily. So as we approach pi by 2, the curve flattens. The curve approaches a flat shape and temporarily, and then again starts to go down. So momentarily it flattens. So if you try to draw a tangent to this orange curve at x equal to pi by 2, you get a slope of 0, and that's what we have here in on the gray curve. Gray curve crosses the x-axis. You get a value of 0. So intuitively you can see that it makes sense. Let's try to now derive it very quickly. So we have just to show that this derivation is not complicated. Once you derive one trigonometric function's derivative, you can appreciate the formula for the others. So we have fx equals sin x, and we need to find f prime x. And f prime x we already know is the limit as h tends to 0 of fx plus h minus fx divided by h, right? So what is fx plus h? Fx plus h is nothing but sin x plus h minus fx, which is sin x, the whole thing divided by h, and we take the limit of that as h tends to 0. Now, here we will use a formula which you must be familiar with, of sine A minus sine B, and that happens to be 2 times sine A plus 2 times cos of A plus B by 2 into sine of A minus B by 2. So, let us use that formula. So, this would be 2 times cos of x plus h plus x whole by 2. So, what is that? That is 2x plus h by 2, and that is x plus h by 2. So, let's write that here. So, this is cos of x plus h by 2 times sine of x plus h minus x whole by 2. So, x gets cancelled with minus x, and what we have is h by 2. So, sine of h by 2 divided by h. Okay. Now, we will take this 2 to the denominator. Okay. And why do we do that? Because we have h sine h by 2 here, and we already know that the limit of sine x by x as x tends to 0 is 1. So, we will use that identity. So, we will split this into 2 limits. The first one is limit as h tends to 0 of cos x plus h by 2, right, and multiplied by limit as h tends to 0 of sine h by 2 divided by h by 2. And in fact, as h tends to 0, h by 2 also tends to 0. So, we can write this as h by 2 tends to 0, and this we know is 1, and here we simply substitute h equals to 0 and we get cos x. So, we get this neat formula that the derivative of sine x equals cos x, and similarly you can derive the derivative for cos x, and it happens to be minus sine x, and you can again see that from visual inspection that as the slope the value of the gray curve is nothing but the slope of the tangent on the orange curve. Okay. Now, this gives the list of the formulae for the derivatives of various generic functions, constant function x, x times constant, x raised to the power n, and so on, various trigonometric functions, and each of them you can derive using the basic formulae in the way that we just did. Now, let us look at some rules of the algebra of derivatives. What happens when we add 2 functions? Now, here u and v represent functions ux and vx. In short, we are writing them as u and v. Okay. So, what would be the derivative of the addition of u and v? Well, as you might have guessed it would simply be the addition of the 2 derivatives. And what would be the derivative of the of u minus v? Well, it is u prime minus v prime, and we can express the same thing in terms of d by dx like this. Similarly, what would be the derivative of the product of 2 functions? Well, that is u prime times v plus u times v prime, and we can express that in terms of d dx here. This is the derivative of the quotient of 2 functions u by v, and of course, we already know that this would hold when v is not 0. So, wherever you have a denominator, you must always specify this condition, otherwise the function is not defined. And this has a slightly complicated formula. In the denominator you have v squared, and the numerator you have u prime v minus u v prime, and you can again derive this using the basic formula for the definition of derivatives. We will not do that here, but if you follow that formula of derivative being expressed as limit as s tends to 0 of fx plus h minus fx divided by h, you can derive all of them. Okay, let us now look at some other examples. What is the derivative of sine cube x? Now, this can be expressed as composite of 2 functions, g and h, g of h rather, right, where h of x is represented as sin x, and g of h is represented as h cube, and if you substitute you can get this expression as you can see, and the derivative of that could be expressed as the product of these two derivatives. The first one is dg by dh, so you take the derivative of g with respect to h and then multiply it by dh by dx. Take the derivative of h with respect to x. So you can see here that the dh gets cancelled in the numerator and denominator, and what you are left with is dg by dx, which is what we wanted. dg of h is nothing but df. So you apply that to this expression. So dh cube by dh, because h cube is nothing but g is h cube. So you get 3h square and multiplied by d of h by dx, h is sin x. So the derivative of that is cos x, and then you convert everything in terms of x. So because we have x in the original expression, we should try to get the derivative also in terms of x. So we convert this h in terms of x to get our final answer. Similarly, we have another example here, sine of cos x square, and here we can express this as w of u of v, a slightly more complex composite function, where v is expressed as x squared here, u is expressed as cos of v, and w is expressed as sine of u. And then you might have guessed the derivative of f could be written as the product of these three derivatives, dw by du multiplied by du by dv multiplied by dv dx. And you can see here again that dv gets cancelled in the numerator and denominator, likewise du gets cancelled, and what we are left with is dw by dx, which is the original expression. Okay, and if you use that in this example, you get this. And again, like in the previous case, we convert everything in terms of x, because that's what we have as variable in the original expression. So you convert these u's and v's in terms of x to get the final answer. So this is called the chain rule. So whenever you can express a complex looking function of x in terms of composites of two or more than two functions, you can take these individual derivatives and multiply them. That might be simpler to find out the final derivative. Okay, let's look at some other types of functions. Look at this example here on the top, y plus sin y equals cos x. Now here we want to find the derivative of y with respect to x, dy by dx. Here the problem is that we can't express y neatly in terms of x. So what do? Well, it's not too complicated. You simply take the derivative of every expression on the left hand side with respect to x, and likewise on the right hand side. You take the derivative of both the sides with respect to x, every expression. And then what you try to do is you try to assemble all the terms which have dy by dx together on one side, and take the dy by dx part common, so that you can get some kind of an expression for dy by dx through some simple manipulation. And whenever you have a denominator, you already know that you must specify the condition that it cannot take a value 0. Likewise, for the second example, we do the same. We take the derivative of every term on the left hand side and on the right hand side with respect to x, and then try to assemble all the terms with dy by dx on one side, and then try to express a neat expression for dy by dx, and also specify that the denominator the condition when denominator cannot take a value 0. Okay. Now look at some functions where which can be expressed in parametric form. What do we mean by parameter here? Look at this example. As you know, you might recognize that this is the equation for a circle. Y is kind of an implicit function, but in the sense that we need to find dy by dx, right? We can express y in terms of x, but maybe there is an easier way to find dy by dx. We express this in polar coordinates. If you remember, circle equation could be expressed in terms of polar coordinates. That's what we do here. We express x as square root b times cos theta, and y as square root b times sin theta, where theta is some kind of an angle with respect to x axis on the positive, on the counterclockwise direction. And you can judge for yourself that if you substitute these expressions on x and y, you will find that it satisfies this equation, right. So you can make that substitution. Now we need to find dy by dx. Well, it's pretty straightforward. You take dy by d theta on the numerator and dx by d theta on the denominator. You know that d theta would get cancelled and it would eventually become equal to dy by dx. But we do this because it's easier probably to calculate dy by d theta and dx by d theta, because we have got these simpler expressions. So that's what we do here. We take the derivative of y with respect to theta, x with respect to theta, and finally get the answer in terms of theta. But now we need to convert this in terms of x and y, because that's what we have in the original term. In fact, we need to convert this in terms of x if possible, and here we have written that as minus x by y, but ideally this y also should be converted in terms of x, and you can do that from here. You know that y can be written as b minus x squared and square root of that, and that's what you kind of substitute here for y to get the final answer. And again you specify that the denominator cannot be 0. I did not write that here, but you should not forget that. So what we have learned here is that when you can express both y and x in terms of a common parameter t, then it might be easier to find dy by dx in this manner, by taking dy by dt in the numerator and dx by dt in the denominator, and obviously specifying that the denominator can't be 0. Okay, so let us look at some more examples. We have a inverse trigonometric function here. Now y is sine inverse x, so x can be written as sine y, and this again could be seen as a kind of an implicit function of y, and therefore we take derivative with respect to x on both the sides, and then try to do some simple manipulation to get an expression for dy by dx, and that's what we do here. And we are able to get dy by dx as 1 by cos y, but eventually we should try to get this in terms of x, because that's what we have here. So we know that sin y is x, so we convert y cos y in terms of sin y and then substitute x here to get this kind of an expression. And because we have this denominator, we specify that the condition that it can't be 0. Okay. So for example, here x can't take a value minus 1 or 1, and this must be real. We are assuming that we are operating in the real domain, so therefore x must be a value between minus 1 and 1, not equal to minus 1 and 1, and neither less than minus 1 nor more than minus 1. Okay. Now here we have all these neat formulae for the derivatives of these inverse trigonometric functions, and you can derive each of them in the similar way that we did for the sine inverse x. And the interesting thing to note here is that everywhere we specify the condition when denominator is not 0. Okay, now let's talk about the differentiability of a function. We have already discussed this earlier, but we'll kind of do a more formal discussion and then close this topic for the day. So we have this modulus function here, 3 variants of that. In the first graph here on the left hand side, fx is defined at all values of x. In this middle graph, fx is not defined at x equal to 0, and in this right graph, fx is defined at x equal to 0, but it takes a different value than 0. It takes a value of 1. We have already seen that the first function is continuous and the second and the third functions are not continuous. Let us now check if they are differentiable. Okay. Now this first function we have already discussed briefly that it is not differentiable at x equal to 0, because the slope of the tangent to the curve takes different value when you approach x equal to 0 from the left hand side and when you approach x equal to 0 from the right hand side, right. So what we mean is that the limit of the derivative of f takes different value when you approach x equal to 0 from the left hand side and from the right hand side. So there is no unique derivative value. So therefore we say that it is not differentiable at x equal to 0. It is differentiable at all other points. And how about these other two graphs, other two functions? Well, they are not even continuous at x equal to 0. So there is no question of them being differentiable. So, these other two functions are also not differentiable at x equal to 0, and they are differentiable at other points, just like the first one. So, difference between the first and these other two functions is that the first function is continuous at x equal to 0, but not differentiable. These second and third functions, they are neither continuous nor differentiable. So you might have already guessed that continuity is a precondition to differentiability. Okay, only when a function is continuous might it be differentiable. Okay, so these functions are not continuous because of different reasons. Here this is not defined, and here because the limit of the function from the left and right hand side is not equal to the value that the function takes at x equal to 0. But both of these are not continuous. So therefore, they would not be differentiable at x equal to 0. Whereas here this function is continuous, but still it is not differentiable because it takes a sharp bend here. The derivative does not have a unique value at x equal to 0. Okay, let's try to kind of generalize this into an intuitive feel. Okay, so when would a continuous function be differentiable? So first thing, I hope you've understood that a function has to be continuous. Only then it might be differentiable. A discontinuous function would never be differentiable at the point where it is not continuous. Now, when you have a continuous function like this, where it has a smooth curve, right? In this case, whatever point you take, even the point where it is curving, right? And you try to visualize the slope of the tangent as you approach that point from the left hand side and from the right hand side, you would see that the slope approaches a common value, which is the slope of the tangent that you would draw at that particular point, right? And the same holds for various points that you can visualize on this other curve that I have shown here as well. It does have a unique slope, whether you approach it from the left hand side or from the right hand side, right? But if you look at another function which has a curve which takes a sharp bend, something like this or something like this, right? And you look at the behavior of the function at this point where it takes a sharp bend, and you look at the slope of the tangent to the curve, you will see that as you approach that point from the left hand side, you get a different slope of the tangent compared to what you get as you approach that point from the right hand side. And the same is true here. You get different slopes of the tangent when you approach this point from the left and from the right hand side. So what we say in these two cases is that there is no unique slope, and therefore at those points of sharp bends. So therefore there is no unique derivative, and therefore the derivative does not exist at these points of sharp bends, which means that these functions are not differentiable at these points. So that's what we mean by differentiability. Now look at some more examples. Here this first function is a straight line, so it is obviously continuous, and it seems that it is also differentiable because it does not take a sharp bend. Any point that you take, you get a unique slope, whether you approach that point from the left hand side or from the right hand side. So it is not only continuous, but it is differentiable. The same happens here with the top middle function. You take any random point C, you approach C from the left hand side and from the right hand side, and try to visualize the slope of the tangent to the curve. You see that you will get a unique tangent, which means that f prime x, the derivative approaches a common value. The limit of the derivative exists. It has a unique value as x approaches C from the left hand side and from the right hand side. Whereas this function here, it is an example of a continuous function which is not differentiable. We have already discussed this. And what happens to these functions at the bottom? Well, they are not continuous. None of them is continuous, so there is no question of any of them being differentiable. So they are neither continuous nor differentiable. Finally, let's try to apply some mathematical rigor. Okay, we take this good old modulus function that we have seen earlier. We formally define differentiability. What do we mean when we say a function is differentiable at a particular point in its domain? Well, it should be defined at that point, and it should have a unique slope at that point, which means that f prime c should exist for it to be differentiable at c, which basically means that these two limits should be equal. And what are these two limits? These are the limits of the derivative of f with respect to x as we approach c from the right hand side and from the left hand side. So when we approach c from the right hand side, think of values on x axis slightly more than c, but very close to c. We write that as x tends to c plus. Likewise, when we approach c from the left hand side, think of values on x axis very close to c, but to the left of c, slightly less than c, and we write that as x tends to c minus. So these two limits should be equal, which amounts to same as saying that the slope of the tangents to the curve of f as we approach x equal to c from the left hand side and from the right hand side should approach the same value, should acquire the same value. Okay, and you can test here mathematically as well that the two slopes are not the same. The function, while the function is defined at x equal to 0, the slope of f prime x when we approach x equal to 0 from the left hand side is minus 1. We see that here, right? As we approach x equal to 0 from the left hand side, the slope is minus 1. Slope of the tangent to this curve is minus 1. Whereas that slope is plus 1 when we approach x from the right hand side. So this function is not differentiable, even though it is continuous at x equal to 0. Finally, to end this topic, let's take a look at one more example of this function which has these two terms. And whenever you have a modulus term in the expression of a function, first you should try to get rid of the modulus expressions, the modulus symbols, right? Try to get the function in the expressions which are like polynomials or trigonometric or familiar functions that you can differentiate easily. You already know that they are differentiable and in their domains, and you know the formula for them. So that's what we'll do here. Okay. So how do we get rid of this modulus functions? First, you try to calculate the value where they take they become 0. Okay, when does x minus 1 become 0? At x equal to 1, right? And therefore, we know that for x less than 1, this term x minus 1 is negative, right? So the modulus of that would be minus of x minus 1, right? And how about this one, x plus 1? When does that become 0? At x equal to minus 1. So for values of x less than minus 1, this is x plus 1 is negative. So modulus of that would be minus of x plus 1. And for values of x greater than minus 1, x plus 1 is positive. So modulus of that would be plus of x plus 1. So that's how we get rid of the modulus symbol. And we'll also simultaneously draw that on this x axis. Okay, we'll make these three marker points 0, 1 and minus 1. Okay, and we have these three intervals. Okay, one interval is x less than equal to minus 1. This is the first interval, and we know that is one break point here, right? And the second interval is minus 1 to 1, and then we get the second break point here plus 1, where this one becomes 0. And the third interval is x greater than plus 1, and we get rid of the modulus symbol for these three intervals. So let's try to understand the first one here. So for this first interval x less than minus 1, we have seen that x minus 1 is negative. So when we take the mod of that, we write it as minus of x minus 1 to make it positive. And x plus 1 is also negative, so we write that as minus of x plus 1 to make it positive, right? And likewise for these other intervals. Just to understand this second one here, when x is between minus 1 and plus 1, x minus 1 is negative. So when we take the mod of that, we write minus of x minus 1, whereas x plus 1 is positive in this interval, right? Because we are talking of x, values of x greater than equal to minus 1. Right. So x plus 1 is positive already. So when we remove the modulus, we keep it positive, plus of x plus 1. And therefore, finally, we get these neat expressions for these three intervals. And let's try to draw a diagram of this, the curve of this. We will draw a y-axis, and then we will try to look at what happens at x equal to minus 1. As x approaches a value minus 1, we will take 2 points here on the y-axis, 1 and 2, let us say. And what happens at x equal to minus? As x approaches minus 1, you see that this value approaches 2, right? And for values of x less than minus 1, it is a straight line with a slope of minus 2. So the curve would look something like this. Something like this. the slope of minus 2, and we are talking of an interval less than minus 1, not equal to minus 1, so we draw a hole here, right. It just approaches this number of 2. What happens in this interval, minus 1 to 1? Well, at x equal to minus 1, this takes a value of 2. In fact, it is 2 throughout, so it's a straight line. So we are talking of minus 1 to 1. So we have a straight line like this, and here we draw a hole again. Why? Because this interval includes minus 1, but it does not include plus 1, right. So it stops just short of plus 1. And what happens in this third interval, x greater than or equal to 1? Well, at x equal to 1, it becomes 2, and thereon it is a straight line which takes a slope of plus 2. So we write that here. We try to draw that here as a straight line, and this one is defined at x equal to 1. Okay, so now we have a function which is defined at all the points, but as we can see visually that it is differentiable everywhere except probably for these 2 points, x equal to minus 1 and plus 1. Why do we say that? Because as we approach minus 1 from the left hand side, we get a slope of minus 2. That's what we have here, right. Whereas if we approach minus 1 from the right hand side, we get a horizontal flat slope of the tangent to this green curve, which is the slope of 0, which is a differential of this constant 2. So we have 2 different values of f prime x. So what we say is that f prime x does not exist at x equal to minus 1. And the same thing happens here. If we approach plus 1, x equal to plus 1 from the left hand side, the slope on this curve is 0. And if we approach x equal to plus 1 from the right hand side, the slope of the tangent on this green curve is plus 2. And therefore, this is not differentiable at those 2 points. Even though it is continuous at all the points. Okay, with that we end the discussion on continuity and differentiability, and you see that, let me just remove this diagram here so that you can see the mathematical treatment of what we have just discussed in this example. I am not going to repeat it again, but just have a look at this so that you can follow in the light of what we have discussed. At these 2 points, x equal to minus 1, we have estimated the limit of f prime x as we approach minus 1 from the left hand side and from the right hand side, and we see that the 2 limits are different, so it is not differentiable. And the same thing is what we observe at x equal to 1. The 2 limits of f prime x are not the same. So what we see here is that even if we do not draw the diagram of this function, we can still calculate, find out whether it is differentiable or not. Even though drawing diagram makes it simpler to visualize, so it is always advisable to do. Okay, so what have we learned in this session? We already learned in the previous sessions about continuity, we looked at the definition of derivatives, and in this session we looked at several examples to understand derivative much more clearly. We have derived certain formulae for certain kind of functions. We have got a visual feel of how to appreciate the derivative on a graph, and we have looked at this notion of differentiability, how to check whether a function is differentiable or not at a particular point. Okay, so I hope you enjoyed this session, and you would practice enough problems to master these concepts. A lot of practice is required. Please note that the concepts of continuity and differentiability form the basis of this vast field called calculus, which has applications in many fields in the real world, in engineering, in sciences, in economics, and so on. And therefore, it is a very useful subject to learn, not just for your studies, but even for your future profession. Okay, so with that, let me say goodbye, and I will see you in the next session. Okay, bye bye.